Welcome to Prevented Podcast, a blend of tech and leadership. Our guest today is Bert Wank. He's a veteran of power semiconductors and renewable energy. We were talking just before starting recording, the tales of two brains. If you want to share that to the audience before we talk a little bit about infiniRel, his company, but I think this is a good conversation starter, right?
Well, yes, actually, I can't take any credit, and thank you so much, Federico, for having me. I was fascinated with Mark Gunger's presentation of the tale of two brains, how female and male brains process information differently. That on the one side, the female brain has everything connected to everything else, like the kid, to the husband, to the home, to the car, to the job. And then the male is very focused on one thing only, making only sure you focus on one thing, and once it's done, then you focus on the next thing. And so now you can see the dynamics between those two brains trying to process information differently. And that I should have watched that way before I got married. Anyway, that was hilariously presented and very useful information for anyone that's interested in relationships.
Yes, so we not only we cover technology, but also we cover relationship advice, right?
Yeah, actually, a company is actually like a marriage, and then you have investors, which is like a marriage, and it has very similar dynamics. So that's actually a nice little segue that these things are in fact connected, just in different plateaus, but they're still connected. Still very useful.
Yes. I at one point I thought about the idea of balance, but you cannot achieve balance all the time because balance means that you have 50% on one side, 50% on the other, right? And that, that's almost impossible to do, right? And I like the concept of harmony. With the idea of harmony is that everything works together in like a concert, yes. Right? And that doesn't mean, balance. That means, sometimes you spend, time with your family, right? That means you spend 100% of your focus on that, right? And then sometimes you spend some time with, investors, right? You have multiple relationships, right? With clients, with employees, right? And all of them, they require 100% of your attention at that time, right? That kind of breaks the balance, but also if you think it in terms of harmony, it's it's a much more sustainable concept, I guess, right?
And I like your thought about the harmony and balance, because as long as you have a feedback system, something that feeds back where you are, or the signals that you ideally want to have, and you're a little bit off, you feed that information back so you make a correction. It's the same way as in technology. When you have really nice, clean audio recording, there's a nice, tight feedback loop that makes it very precise. But same way, if your gives you feedback, well, you better take a note and adjust your behavior so it actually becomes a harmony. And harmony is back in the frequency, right? It's actually an intrinsic frequency of the system. And this is actually a really nice segue to what we are doing at infiniRel, because when we're looking at electronic systems, then they have to be also in harmony. And we've seen that when they become out of harmony. I mean, just even lately, it's the Spain blackout. It was a disaster, right? It was completely out of harmony. It was disrupted, and there was no feedback in time, and the control system wasn't working anymore. So that was an evidence that was exactly to your story. And I think the true mission for us is to assess those various frequencies and seeing where it is imbalanced, and then flagging the imbalances early enough so you can take action, right, to prevent major disasters. That's kind of at a very high level what we do. And really in this monitoring part, I think of it as an EKG. We actually have, in order to be very precise when it comes to electronics, and we are literally electrifying everything these days now. It is, these processes are so fast that you need to look very, very fast, much faster than old school traditional systems. And that's like you think about it as the heart of the system has a heartbeat. But to assess the health of the heart, you got to look at the noise when the heart starts pumping, right? Since it's in the noise where you see if there's any arteries that are maybe clogged, or veins, or something else happens, something is not proper. And you see this in the wiggles in the signal that is indicative of a heart failure. And that's actually what we built. We built an EKG to actually measure those wiggles in the electricity so that we can tell the telltale signs, oh, something is wrong. What is this? What component has caused this disharmony? And then we can flag it, and then essentially being the doctor, we can say, okay, now we can fix it before it actually literally blows up.
Very interesting. So what you're doing on infiniRel,
yeah,
what you're doing is you're building a monitoring system so you can detect errors before they happen, right?
Exactly. Yes. And we're focusing on electronics, right? So traditionally, the concept of condition-based maintenance has been around for like at least 40 years, right? We've been looking at bearings and motors and generators. Aircraft turbines have that. So that's actually a very easy to follow system, because if a bearing goes out of whack, you can feel it vibrating differently. It heats up more, so you can feel the touch. It gets hotter, possibly even smell the oil burning off, right? All these human sensories are there before it actually is disintegrating, right? So there's lots of time left to do a repair. Now in electronics, if any of those human senses are triggered with electronics, if you smell electronics, hear electronics, touch electronics, anything happens like that, it is too late. So we got to have a very different system, much faster, much earlier, to actually detect before things go wrong. That's our mission.
Interesting. Yeah, I mean, I studied industrial engineering, so I kind of understand what you're talking about bearings. So the bearings can last many, many years, but at the moment that the truck has a very tiny damage, then every time it turns, the bearing keeps hitting and hitting and hitting there, and the damage grows exponentially. And then, you can hear it, you can feel it, the vibrations, the heat, you can listen it in the car without all the other noises. You can actually listen in which bearing is actually failing, right?
Yeah.
So yeah, I understand that concept, and you can hear it like coming up until actually breaks, right? We had an issue with it was a brand new car, and one of the main bearings of the accessory belt got blocked, and then we had to literally tow the car out because it broke the belt, and then the car was
yeah, then you stop.
it was impossible to move. Yeah. And it speaks about the low reliability of this type of cars, right? Anyway, coming back to infiniRel, right? What is the relationship between what you were describing on the microprocessors and the electrical grid, right? Because on the electrical grid you have the issue of feedback loops, right? Where you have
there's always feedback loops.
Right. You need to put all the engines in sync, right? And then if you feed energy into the system, but everything is down, now you have peaks of consumption that basically, you have to follow a very precise synchronization to start everything again, right? So I'm wondering,
move a little bit.
Yeah.
Yeah, so sorry, I wasn't sure if you hear the noise, but let me just go to a different room. So let's.
It's all good.
Okay, this might be a little bit better. Sorry, but yeah, you're following the concept very well.
It's the beauty of working from home. Yeah. The family is going to show up sometime at the calls. It is all good. Yeah. So I'll ask the question again. I was asking about what is the relationship between infiniRel microprocessors and the idea of when we have the grids, we have so many components, right, on the grid, like a nationwide grid, right, electrical grid. And then you have to put all the engines that are generating, all the alternators that are generating electricity, they have to be on sync on the wave. And then if you start some, but then you have peak of consumption somewhere, you have to follow a precise order to get the grid up to generate. I'm wondering what's the relationship between.
Yeah, and that is let's start how the system used to, or it still is working, like traditionally in a 100-year-old grid. You have generators that are steam driven because of gas turbines or coal, but we try not to do coal anymore, but so there is a rotating mass, and the rotating mass carries through if there's any disruption on the grid. And so the inertia, the sheer inertia, just makes it keep on going. And in the last few decades, as we have moved towards the renewables, like solar and wind, and now batteries become very, very important. In order to get that type of power to the grid, we use electronics, and it's typically called the inverter, because they start out as technically it's a direct current, and in the grid we need alternating current. So the inverter does exactly that. And inverters are built with semiconductors. And semiconductors work very, very differently than the copper and steel and wire machines that weigh a ton. And they, in fact, have also a lot lesser margin, right? So if you have a motor generator, you can, for a short time, you can get double the voltage on this thing. It won't like that. It'll not have a 50-year life anymore, but it will sustain it for a while. In electronics, you have a very thin margin, maybe 20-30% of margin to have a voltage spike. And then you're walking on thin ice because these chips are so small that a little arc just blows the thing up. And it goes really, really fast. It's like less than a microsecond. And that's the challenge, right? So you have a very harsh grid and a very sensitive semiconductors. And the cost, you can make it more robust, but there's an exponential cost to make semiconductors be rated at higher voltage than they normally operate, just in case there's a spike. And energy is a commodity, so it's very cost driven. So the margins are rather thin, and then you have very harsh environments. You've got temperatures that are sometimes insanely hot and then also freezing. You've got moisture that is oxidizing your metal, which is the conductors, and all these perils add up, and that leads to a premature failure. So the saying is, oh, there's no moving parts, it should live forever. Well, that's a fallacy. It's actually the opposite is true. And so when we come in, we actually monitor the fingerprint of those disturbances, capture those, and find out what stress has it caused on the electrical component. And then if that stress, we digitally accumulate that and evaluate how close is this to a failure. We can raise an alarm flag saying, you're walking now on borrowed time here. It's time to replace that semiconductor or that capacitor, that element that is stressed out.
Interesting. I used to play with LEDs, and every time I would not put the resistor, right? You have to put a resistor in series to the LED to avoid burning it down, right? And then, when you're tinkering with it, sometimes you forget, right? And then I will blow out the LEDs. And it was like, pop, instantly.
Yep, exactly. That's how it works.
So the same thing happens with the, yeah.
Yes. And now you integrate both now on the grid, right? You have the old systems and the new systems. And they have to work together, which is going back to your theme of harmony. It's very disharmonious. You have one system fighting the other system, and so there's new technology approaches to do this grid following and grid starting inverters, so they actually can start electrically, they can start the grid. And it's not trivial because everything has to be synced up in harmony to the European 50 hertz or the 60 hertz in the US. And that's not a trivial task. So we have to have, literally, we have to have intelligence where it's needed, like locally. And that means, again, processes to assess what needs to be done on a microsecond level to not have a grid being challenged with a disruption. That's actually where the avenue we're going, right?
And I believe that there also has been, I think it's in Holland, I could be wrong, where they build these enormous wheels, inertia wheels, so they could feed the grid and take out of the grid without taking too much into consideration the phasing, right? They can be a little bit off phasing because the wheels take care of the compensation.
Yes, these flywheels. Yeah, these flywheel systems are very, yes, and that would be the technical term. But yeah, they have been used certainly on very high power application. They store an enormous amount of power, but not as much energy. And it actually also goes back down to our earlier discussion about bearings, right? Since the typical flywheels are very large, But then we have to remind us that the energy actually is a square of the speed. So it actually makes a lot more sense to make the wheel spin twice as fast than make it twice as big, because you get then 4 times the amount of the energy when you spin twice as fast, versus when you make it twice as big at the same speed, you only get twice the energy that is being stored. But it is a wonderful system for localized storage.
Yes, you're talking about the angular momentum.
Yes, exactly.
It's
And guess
mass
what?
by p
Right.
p
And
square.
then, and the other beautiful thing for us is that a flywheel, because it's operating at different speeds, when it operates as a generator, as it slows down, the frequency goes down. So you can't use it directly to the grid. So you have to first rectify it with power electronics. And when you have rectified it, then you have to invert it again to the nice 50 or 60 hertz. So there's now 2 power electronics systems at work in a flywheel. Right? Again, it's part of the big electrification part that is happening. Power electronics is now everywhere.
Right. I got into sorry, I'm digressing to another topic, but I got recently into an original Otis elevator, right? So what happened is that it actually has 2 speeds, but it only has like 1 speed, right? And then it's all mechanical, and it has a big spring that you can feel it when it moves, right? To kind of compensate the initial push, because it goes from 0 to everything, and the motor was, we rented an Airbnb, an apartment, and the electrical motor was right next to the apartment, so we could hear it during the night and the day, right? And you could hear when it was like starting up at it was trying to catch up to the frequency of the grid, right? And then it will do continuous sound once it gets to the actual speed, right? But then the acceleration, it was done by springs, right? It was a progressive spring that you could see, because the whole elevator was a cage, open cage, so you could see the walls moving around
Historic
you, right?
one. That's going to be fascinating seeing
Yeah.
that at work.
It's from the 1930s, right? So it was fascinating, for me as I'm a software engineer. We never see the things moving, right? It's like zeros and ones, right? So here you can see the things moving, that you can hear the clickings and the everything, right? So anyway, it was fascinating. And then I go to a modern elevator, and it has these phase shifting engines where, it accelerates, and it has infinite speeds, right? And it goes right to the edge of the floor, and then it stops. Very subtle, right? So it's we were talking about the facing, right? That's how kind of I connected that, right? So so anyway, that's what I was thinking about that. So tell us a little bit more about infiniRel. What are you doing? I understand you raised some funds. You got some grants. You got some prize rewards.
Right. Yes. So as a startup, right, we're always on the hunt for support, financial support, and believers that the mission that you're on, in our case, literally it's infinite reliability. That's where infiniRel, the name, comes from. It's if you have perfect knowledge about a system and its future, and you see it failing, if you see it early enough, you can change the future. You can change the path you're on, right? So you can correct it. Also in electronics, and that's the part where we looked at, or actually when I was back in, still in semiconductors, that's my background, and I learned from a presentation by the head of the Department of Energy, Dan Ton at the time, that inverter failures were contributing 59% of all unexpected maintenance cost in a solar plant. I thought, that's a problem. That's really what started us to think about, well, if solar is going to be growing and growing and growing, which it did, then this problem will also be growing unless we fix it. So we set out to look at the cause and effect. And that's really where today's technology, what we call AI, or derivative of that is machine learning, comes to play. When we recognize pattern and we see those patterns fast enough and can anticipate and predict them, then we can change the outcome. And that's where our predictive analytics technology is coming from. And where we focusing on initially in our market entry was the two systems, the solar plants, but more importantly, battery energy storage systems also use inverters because the batteries need to be charged and discharged, and that's done with electronics. And in contrast to solar plants, battery energy storage facilities have to run 24/7. In the solar plant, you worry about once the sun rises until the sun sets, that's when it needs to work. But batteries 24/7. And so that's where we developed our EKG, our energy cardiograph, and we have now had the chance to work with a very large battery energy storage developer and with a solar operator of these big plants to actually go out in the field, into the desert, and do what we call the inverter health scans, where we take the heartbeat of the inverters and analyze what is happening inside. So we can advise our clients on the risk of failure and more specifically what elements of the system of the inverter they need to be replacing before it actually costs them a lot of money. Uptime is the name of the game. Units that are up, it's an asset, so it generates revenue, it generates electricity, which is revenue. If it stops doing that, you lose revenue. When you lose revenue enough, then actually you might get even more penalties on top. A long tail of financial losses associated with it, and it's been degrading over the years. I mean, in 2023, the last number I got was that the United States of America's solar industry has lost $4.5 billion in preventable losses, and the lion's share of that is the inverter that stopped operating or literally sometimes catastrophically imploding. And that's the part that we're focusing on to avoid as we continue with the electrification of the grid. There's charging stations using power electronics, electric vehicles use power electronics. This afternoon I'm going on to witness an electric plane here in Palo Alto. So I'm pretty excited to go there because, well, if plane's power electronic fails, well, that might become a glider, and some planes glide well and some planes don't glide well. So it's a risk. It could be a life and death risk, right? And so these are all applications that our prognostics at certain time of maturity we can actually address.
Right. And with the issue with electronics is that you cannot open it up, inspect it, like you do with preventive maintenance on, internal combustion engines, right? On airplanes, right? They have to certify every certain hours, every certain, time. There is no known path for that type of certification for electric airplanes, right? At least not yet.
Not yet,
So
exactly.
infiniRel, right? So infiniRel will be a good solution for that specific case study, right?
We're definitely working towards that, right? So right now our EKG is in a rather large format. That's why we're looking at large power plant where like a single EKG can avoid 5, 6 in the orders of magnitudes of damage. $100,000 avoided is a value, but in flight, anything that moves, particularly flights, things have to be very light and small. And so eventually we want to shrink our EKG to chip level. And that's going to be the game changer because then we can be immediately on the printed circuit board, in the electronics, on the inside. We can be the brain of it. We can actually operate the power electronic system so we make it intrinsically safe. That's really the vision I have where we need to go. In the meantime, we need to collect a lot more data so we know exactly how we architect the system as we shrink it to a small and very affordable size. Imagine when your car actually is reliable. You don't have to be afraid that it stalls out. That's the point.
Right. But the benefit with the car is that you can stop at the side of the road and you're going to be fine. Right, but with an airplane, you don't have that luxury.
Then
right?
It is exactly, that's a mission critical part there. And then you're talking about space. I mean, one of the exciting parts that I learned recently about is since we now the press is full about AI and data centers are so power hungry, and can we get the power, and then where do we locate the data centers, and then of course there's data security involved, and which countries are involved. And now imagine we have data centers in space. Actually, there are half a dozen companies that work on data centers in space, and they need to be reliable too.
That would be amazing.
So that's actually the one thing I'm currently reaching out to find out if there's an interesting avenue to accelerate our roadmap since in space, things have to go to chip level. So if we could have a partner in that area to say, hey, we need a chip like that, so we know that when we have to replace a data center, pretty much a satellite, before it actually starts failing, we can plan that weeks ahead of time because, right, logistics, it shoot up rockets like ad hoc, you have to plan all these things. That information would be very valuable to do. So that's actually an exciting part for us to consider as our partner development strategy. So if there's any listeners that work on data centers in space, please reach out to me at bert.wank, that's W-A-N-K, at infiniRel.com, because that would be a great discussion to have.
Great. And we'll put your contact information on the notes of this episode so people can reach out to you as well.
Super. Thank you. I much appreciate that, Federico.
Yeah, absolutely. Happy to help. So what other plans do you have for infiniRel? What are you planning to do, in the next 12 months?
So with the end game, the next part is we need to get access to a bunch of more plans. We need to spool up our data, right? So that's really where the machine learning, you need to have, again, right, the harmony, the frequency, the feedback from the power plants. And so we're looking for the early adopters, the handful of companies we can work very closely with to roll out our EKG technology, be on site, and then follow the life of the inverter along. And we will see some failure along the way, and that's exactly the valuable information that we need to feed back in the system. Have we detect that failure risk before? So that's an affirmation, a feedback, yes, we're on the right track, we saw the right parts. Or have we not seen it yet? Then we need to change the algorithm. So that's really in our next immediate steps to roll out the next 12 months. And then building more EKGs. So we're currently also in the fundraise, so we can build some more of those. I'm also in a supplier discussion to shrink the first generation so we can be a lot more liberal in deploying EKGs when the size and the cost is a factor of 10 smaller, but at the same time the performance actually goes up another factor of 10, right? So it's actually a merit increase of a factor of 1,000. So that's pretty exciting, and I'm looking for the right partners for us to move into that next level of maturity where we can deploy EKGs more liberally in those battery and solar facilities, particularly the ones that might be powering data centers, because that's part of the mix.
Right. Very interesting. So I wanted to ask you more a question about what advice would you give to a young engineer that would like to get into the superconductor industry or follow your steps? What advice would you give them?
Superconductors are actually a fascinating topic. We've been pushing the boundaries on high temperature superconductor, but actually it's not really related to a specific area in general. Just follow your passion. I think that's a driver, because we will always see, as we push our boundaries, we will always see obstacles. And to overcome those, we have to have that internal drive, right? That internal motivation, right? That quest. Rather than being pushed or nudged by friends and family to something that you may not really want to do, but you just nicely, kindly have to correct, and you have to focus on what drives it. In fact, there is a Japanese term for the professional fulfillment. It's called Ikigai. And you find that actually on my LinkedIn page as part of the images, where you have 4 quadrants, and when they overlap, all of them, then that's your Ikigai. That's the sweet spot of your professional fulfillment, which means you do what you're good at, because if you're not doing what you're good at, then it creates the fear that someone else is better and you're out of a job, right? So the avoidance of negative emotions is part of the game. The second part is you do what you're passionate about, because time is irrelevant, right? Time just flies by and you have so much fun, you can't wait to do it again, right? And that's really important, because if it's not the case, then you just check your watch and it's like, oh man, when is this job over? I want to go home. Well, that's not fun, but you gotta have fun with it. And the third one, which is also important, that you have to have a human purpose. You touch someone in this world. It could be the world in itself. It could be one person on this planet that you touch with your solution, that you improve. Because if we're not doing it for some other human being, even indirectly, it feels empty. We're not feeling fulfilled. If it's just stuff, it just doesn't have the same value for us intrinsically. And so that's also very important to have. And the last one, of course, it has to have some value so someone actually pays you, which is the hardest part of this startup to overcome, at least initially, right? The payout is usually at the end, when you see it all the way through. But when that happens, in the meantime, there's lots of iterations and, a lot of failures, a lot of corrections, a lot of feedback, right, to bring back into harmony, which I really like that you started out this whole subject on the harmony line. Yeah, that would be my advice. AI is super, it's like one of those big, big things to absolutely pay attention to. It's like the internet was, we're just at the tip of the iceberg to see its true potential. That's big. Power and energy is very fundamental still in power electronics. Understanding analog systems is equally important as understanding digital systems, and usually it takes two different type of personalities. There's always exceptions, but if you have a quest for analog, just go down the analog path. Systems are by and large analog, but digitalization helps incredibly efficiently to work with analog systems. So it really takes both. It's a symbiosis of both analog and digital. And there's always an intersection, an exchange between both sides. And that is also good to keep in mind for any follow-on generations that want to engage in the world of energy and electronics or power and even generically follow the passion.
Right. Very interesting concept, the
EKG, the energy cardiograph.
Yeah, and the 4 quadrants that you were talking about. Very interesting concept.
Yeah, when I saw that, it's like, that makes sense. We get usually stuck in 1 or 2 quadrants, and then after 10 years, it's really hard to break out, right? And so if you're aware of that early on, you can make adjustments and change the direction that you're going to get a greater fulfillment. Yeah, so it's actually also like, how did you get into the recording side, right? How did this proliferate, right? Until you ended up where you have so much fun that you're smiling. It's like, yeah, this is the stuff I want to do. This is what we enjoy it.
So I got into I'm a software engineer, so I kind of like being focused too much on the technical part, and I've been moving towards relating with people, right? And then I find this format much better to have meaningful conversations. So I start doing this to start writing myself, to start figuring out some ideas that I wanted to explore, and then from there I found that it was much more interesting to have it with different people, right? Because you can have these meaningful conversations that you cannot have on a conference, or you go to different events. I was in Santa Clara Convention Center on February or March, and you meet so many people that you get overwhelmed, right? So
yes,
being able to have this space where we don't have too many distractions and we can just have more meaningful conversation, that for me has been kind of why I got into this and why I've been enjoying it more and more, right? Because then, as you mentioned, like the times flies by so quickly that then we just I have a lot of fun, and I feel that the guests have a lot of fun as well. So that's kind of how I continue.
So you found your Ikigai.
Yes.
Very good. Congratulations.
So yes, it's very interesting, yeah. And my first job, when I started my first job, I was saying I would do this for free. It's great that they pay me for it, but I was having so much fun getting into code and all that stuff that I was thinking I would do it for free. It's great, they pay me because now I have more resources to do more of what I like, right?
Exactly.
So yeah, I completely agree. Yeah. So thank you very much, Bert, for being here, for joining us. Unfortunately, we ran out of time. I don't want to overstep of our schedule.
That was great. It was great to have a chat, Federico. I appreciate it. I thank you too for the opportunity. And when you're back next time in Santa Clara, the Bay Area, just come look me up. There's a good chance I'll be around, and then we can have another chat over a cup of coffee or tea.
Sounds like a good plan. Yes, we'll do that.
All right. Great. I appreciate it.